magic.
Let's see.
Where it turns out to be the remnants of. And then we just solve for the bits of gamma. I'll spare us the details, but this is the result.
So I was thinking about this a little bit, and yeah, with the bits of gamma, it's kind of like
just solve.
It's kind of like going from this step to the next step. Right here, you're just thinking of gamma as like a real number, and I guess y is like a real number. But then when you go to this step, so you kind of started off gamma was a real number, but then you went to like this thing right here where you're talking about like the mantissa of gamma and the exponent of gamma. Now you're kind of thinking in terms of I don't know. We just kind of did this like trick here where we had like gamma is equal to 1 over y. And then if you just kind of do this isn't quite like equality, but it is kind of. It's like the mantissa of gamma plus 2 to the 23 times the exponent of gamma is equal to 1 over mantissa of y plus. So this is kind of like a weird step to do because are we saying that you're saying gamma is equal to the mantissa of gamma plus 2 to the 23? Is this true? Like the actual number gamma is equal to this? This is a weird step where we kind of like replace like the real number with 23-bit kind of like representation of that number. It's kind of a weird step. It kind of makes sense, but it's also just kind of weird. It's kind of like you start off gamma up here, and then you go down to, yeah. There's one point in the video where it's like early on where he kind of says it's good to think about these numbers in terms of a specific way. It's this.
But before we start with these 3 steps, let's first take a look at binary numbers. We said that in the first line, we declare 32.
It's here.
For this algorithm and for the rest of this video, it will be useful to think of the mantissa and the exponent as the binary numbers they are. If we have given 2 numbers, one being the mantissa.
Yeah, that was it, but that's not addressing what I'm dealing with right now.
One being the intuition behind the second step is the division in there. Played log of 1 divided by F37590F here again. Well, because our logarithm is actually scaled and shifted. So let's calculate and understand where it comes from. Let gamma be our solution. Then we know that log of gamma equals to log of y to the power minus a half, which equals to minus a half times log of y. Now we replace the logarithm with the bit representation.
Yeah.
And then we just solve for the bits of gamma. I'll spare us the details, but this is the result.
Maybe instead of kind of doing, I don't know if it would be helpful if you just say, instead of saying like gamma is equal to, the mantissa of gamma plus 2 to the 20th. It's the exponent gamma. Instead of saying that, maybe we could say like gamma is equal to, because this is like a real number right here. And then what if we say like b of gamma, which is a member of, this is like a 23-bit, this is like 23-bit floating point representation. Which is which like these two things are definitely equal, but from this to this, gamma could be like 2.132, but then this bit thing could be like 0.011110001, where this is like, this is like the exponent part, and this is like the mantissa part, and this is like the sine part. I feel like I might have to even ask ChatGPT about this. Like, the real issue is like in algebra when we're kind of doing equality and we're kind of converting it to another form, which is a different representation, but like refers to the same thing. It's almost like, I don't know, it's almost like we have this platonic like ideal of gamma thing, and there's different representations of it. There's kind of the real number one, which is like 2.132, blah blah blah, and then there's the kind of like floating point thing. This is a member of, and I mean, there could also be another representation, which is, 2 times 2 blah, 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 2.132 times 10 to the 0 or whatever. This is like just like scientific notation. These are all different ways to refer to the same thing, kind of, basically. So when you say two things are equal, if you said, I feel like there's like a distinction between like a representation and an encoding. That may be like a distinction that's important here. You have the same number, but you just like encode it in a different way. I don't know. If you just had like, just say we're talking about like 1/2 here and 0.5, for instance. Like this is a member of the Q, the rational numbers, and this is a member of like the real numbers. And if you think about how to like encode this on a computer, like this encoding might be like a class of a rational, and this thing might be like whatever class of an IEEE float. I don't know. So They're the same number, but they're just encoded. Well, I guess there's two things. They're members of different sets. And they're encoded differently. But right now, we're basically saying like the set and the encoding is basically 1-to-1. Like that's how we're kind of imagining it right now. We're just saying we're going to encode rationals one way and we're going to encode real numbers one way. But we don't have to do that. These refer to the same numbers and we're just encoding them in a different way. So if you say gamma is equal to the bits of gamma in a floating point thing, that's just a number. That's just another way to refer to the same exact number, assuming that you can represent it with 100% precision. Yeah, just, that this is equal. So like this thing here is like equal to gamma. So if I say, gamma is 2.132 versus gamma is 0.1110010, this thing, we have like sine, you have like the exponent. These two things are the same exact thing. You're just viewing it differently. If I say 1 is equal to 1/1, these are, even though this is a different thing and it's encoded differently, like it does still refer to the same thing. It's just one whole thing. So yeah, I mean, you kind of start off saying 1, you could say that that's equal to the bits of 1 in like a IEEE float thing. Yeah, I don't usually think about encodings. Yeah, that's a whole thing. Like, I guess when we're just doing math, we're not really thinking of how stuff is encoded. We're just thinking of different representations of stuff. I mean, if you say 1 is equal to 1/1, which is equal to, the integral of, from 0 to 1 of 0 to 1 of, I guess it's just 1. Like dx like that, like this is equal to this, like all these same things just refer to 1. It's just like one whole thing. This expression evaluates to 1. This thing evaluates to 1. This expression. So if you say the bits of 1, that also evaluates to 1. I guess I would say. So weird.
The number turns out to be the remnants of the error term mu, the scaling factor, and the shifting. Now we have the bits of our solution, and we can just reverse the steps from the evil bit hack to get back the actual solution from those bits. Well, actually, not the exact solution, just
so going back to this,
from and we think.
So we got that So this basically says that gamma is equal to 1 over the square root of y is equal to this expression, which is equal to this expression. So, I mean, this is our answer here. Yeah, I mean, that's just the answer.
Now we have the bits of our solution, and we can just reverse the steps from the evil bit hack to get back the actual solution from those.
Yeah.
Well, actually, not the exact solution, just an approximation. This is why we need the third.
Yeah, so the Newton thing. Yeah. So I guess we could kind of like do this in code. I'm trying to think of anything we can do at this point to just kind of get a more cool, like grounded, more concrete understanding of this. And we could at this point kind of go through this kind of thing.
And we replace the logarithm with the bit representation.
I mean, you don't know gamma right now. You just.
And then we just solve for the bits of gamma. I'll spare us the details, but this is the result.
I mean, this could be an interesting thing just to write out in code and just see that this is equal to see that this is equal to y, or I guess I. It's called I in the code.
The magic number turns out to be the remnants of the error term mu, the scaling factor, and the shifting.
Yeah.
Now we have the bits of our solution, and we can just reverse the steps from the evil bit hack to get back the actual solution from the.
It's cool that, okay, so let's just see. So now we have I, like this is the answer that we want. This is, but it's still a long type. They are the actual bits of the floating. By the way, how have I not liked this video up to this point? Okay. So I is the bits of like the floating point in there, and then we just like convert it back to a float. So that's good. I wanted to say like now we went back to like a real number from like the bits of the 23 or whatever, but that's not the case. Like we're still the same exact bits. It's just we're just viewing it as a float now instead of a long, so we can't directly manipulate the bits anymore. I don't know if there's any interesting thing to say about the long thing here. These are just bits that we're dealing with, but we're treating them as a float, and yeah, now they're kind of like a float thing. Yeah. Okay. Yeah, that's cool. I guess, yeah, it would be kind of interesting in code to kind of like unpack this step and kind of do some stuff here. I feel like I might be a little less interested in unpacking this part with code, the 3/2. It's just like Newton iteration thing. Maybe once we get there, that might be interesting. But yeah, I think in the next stream, it'd be cool to take, just in like a Jupyter notebook, kind of unpack this step a bit. Maybe kind of like reverse it a little bit. We kind of like end up with this number, but then we can like expand this to that big expression with the like 2 to the 21 over 2 to the 23 thing, blah, 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 all those yeah, we can just evaluate that expression in a Jupyter notebook. Yeah, it might be interesting. So we'll do that then. Sounds good. See you guys then next time. Bye bye. Peace.